All right, so let's pick it up where we left off. Um, Here we go. Rates of change. Yes, I started to mention this the other day that this is going to prove to be a hugely important topic in calculus when we start getting to the new material. The rate of change is basically a way of deciding or explaining how much one variable reacts to a change in another. Okay, I mean, that's really what it is. So here, for example, what we're interested in is figuring out if X changes by some given amount, what impact does that have on Y? So we formally define a rate of change as the change of output, meaning the value Y, given a specified change in X, which is the input. Now, you recognize this formula. This is just the slope of a straight line. It's the same exact concept. Okay? In other words, all we're doing is trying to figure out what is the impact on Y, which is, of course, the dependent variable when there's a given change in X, the independent variable. Or we can rewrite this as y2 minus y1 over x2 minus x1. Or we can write it as f of x2 minus f of x1 over x2 minus x1. They all mean the same thing, of course. All right, here's a very simple example. Suppose we look at the history of the price of gas, and in 2009, gas was selling for $3.29 a gallon, and now well, let's say it's currently 2019, it's selling for $3.49 per gallon. What is the average rate of change over this period? Well, it's pretty clear that the total change is 20 cents per gallon, and this took place over a period of 10 years. So we need to think about it this way. The year or time is the independent variable, or X, because it's the passage of time that we're assuming is responsible for prices changing. Okay, so therefore, the price itself, the price of the gas, is the dependent variable, which is, of course, Y. Okay, if you get that backwards, obviously you're going to get the wrong answer. So here's what we're going to do. We're going to think of 2009 as X1, because that's the first year. 2019 will be X2. And then the two prices are, originally gas was $3.29 a gallon. Now it's $3.49. And of course, these could also be rewritten if you want as f of x1 and f of x2. So you can see that we substituted the numbers, we get a total change of 20 cents over this 10-year period divided by 10 years, which means an average increase of 2 cents per gallon. Now, if you notice, we're making an assumption here. We're assuming that the function that connects these two values is linear. Okay, this is intended to be a straight line, or at least approximately linear. And so if it is, then this average change is going to be very accurate. Here's another quick example. Now, this one involves stock prices. The S&P 500, if you're not familiar with it, S&P stands for Standard & Poor's 500. It's an index that represents the 500 largest stocks in the United States. It's a number that we can look at and take it and see at a glance how the overall market is doing. In other words, obviously there's a lot of stocks trading, and at any given time, a large number of them will go up and a large number will go down. But this index gives us a sense of how the market as a whole is doing. So when the S&P goes up, that's cause for celebration on Wall Street. Okay, because it means we're making money. So anyway, here what we want to know is, given this information, um, let's say look at the period from 2016 to 19, right? And again, we're assuming that the year in which we observe this information is the independent variable, and the corresponding index here is the dependent variable. So we want to look at these numbers, x1, x2, y1, and y2. And once we have that information all set up, we can easily plug these into our formula, and we'll determine that during those 3 years, the price went up $763.86. And that took place over 3 years. So the average price increase was $254.62 over that time frame. Now we're going to use some functions, some actual functions. Here we were given the information in the form of a table. Okay, but these are still functions, remember, because no matter what x is, it's associated with a single value y. But it's easier to deal with equations rather than tables. And so here, for example, we have a parabola. And that's going to look something like this. Actually, let me make that a little neater. So we want to know what is the change, the average rate of change between x equals 3 and x equals 6. In order to do that, we have to figure out the corresponding values of f of x. In other words, in order to do this, let's say this is x1 and this is x2. We need to know the values of f of x1 and f of x2. So this one, for example, would be f of 3, which is going to be 3 squared minus 3 times 3 plus 5, which is 9 minus 9 plus 5, or just 5. And then down here, we'll have f of 6, which is 6 squared minus 3 times 6 plus 5. 36 minus 18 plus 5 is 23. All right, so we can put these in our graph. So what we're really trying to do is estimate the average rate of change. So what you're effectively doing here is constructing a straight line between these 2 points, and you're calculating its slope. Okay, now it's not perfect, but that's meant to be a straight line that connects these 2 points, and the average rate of change is the slope of this line. And that turns out to be, by plugging these numbers, it turns out to be 6. Okay. So here we've used a case where the function is nonlinear, and you can see that this is approximately correct, but it doesn't perfectly reflect the behavior of this function, but at least we can say that the average change between those 2 points is in fact 6. Now, what we want to know sometimes is we want to look at a function and we want to determine the range of values over which it may be increasing or decreasing, or even where it may reach a minimum or a maximum value. Now, we're going to see a lot of that in chapter 2, I believe, when we introduce derivatives. We're going to only introduce the subject now because we don't really know. We can see how to do this. But it's going to be a lot simpler and easier when we get to derivatives in chapter 2. So we'll start with this cubic function, and we'll take a look at its graph. And again, this is an Excel graph. It's okay, I guess. But it gives you the important details, though. It's pretty clear that right about here, the function peaks out and it starts to turn down again. And here it's the opposite. Now, what's important here is that by drawing a tangent line to the curve here, in both cases, the slope of this tangent line is 0. This is one of the ways we can identify these points. This one is called a maximum point, and this is a minimum point. But because this maximum point is not the largest value on the entire function, we call this a relative maximum, meaning that it's the maximum within this area. Sometimes this is called a neighborhood. In other words, this is the largest value of the function within this area. Although you can see over here, the function does get larger eventually. This is what we're going to call a relative maximum. And so for that reason, we're going to call this a relative minimum. And these are important details. For applications, we often are looking for these points because they can give us a lot of useful information. And what we also want to point out here is that you can identify a relative maximum or minimum, not only by the fact that the tangent line is flat or has a slope of 0, but if you look at the behavior of the function, like here, for example, the slope goes from positive to negative. Okay, so there's in this region or neighborhood, the slope goes from positive to 0 and then to negative. Whereas over here, it's just the other way around. Okay. So in other words, here, as you come from the left, you see how the slope is negative. The slope goes from negative to 0 to positive. So it's like imagine you're skiing. Well, I don't know how that would work with the up part, but as you come down, eventually it starts to flatten out and you start to go back up again. So we can identify these maximum and minimum points. One of the ways we can do that is by observing the change in the slopes of the function as we approach that point. So if we see this pattern from positive to 0 to negative, that means we have a maximum point. If we go from negative to 0 to positive, that makes it a minimum point. By the way, I do want to point out here, although we'll discuss this in great detail later on as well, it may be in some cases we may have a maximum point where the function never goes past that point. In other words, this is as high as the function can get. If that happens, this is known as an absolute maximum. To distinguish it from a relative maximum, and in this case, we would have an absolute minimum. And so again, we'll be given techniques to identify these in chapter 2, but for now, it's enough to note that if you look at the graph carefully, not only is the slope over here going from positive to 0 to negative, but you can see visually that the function never exceeds this value. Over here on the right, it's the other way around. Okay, so we have two types of maximum. Oh, by the way, here's something I've got to mention right up front. As far as spelling, I guess, is considered, these are all Latin words. And so pluralization is a little interesting. First, I just want to mention that the word extrema refers to minimum extremo, sorry, can refer to either a maximum or a minimum. So the word extremum, it means a point that's either very large or that larger than the other points or smaller. The plural maximum is maxima. Again, that's because it's Latin. The plural of minimum is, as you can imagine, minima. And then the plural of extreme is extrema. I just want to throw that out there because it's easy to get confused. It's easy to think of minimums or maximums. No, that's not correct. Maxima, minima, and extrema are the correct terms. Oops. All right. All right. So, oh, that was just meant to be a side note. Okay, let's get back to this. Now, a function can have multiple um, or relative extrema, I guess we'll say, but only one absolute extreme. Okay, no, there's only one absolute maximum, only one absolute minimum, but you can have many relative minima and maxima. Sometimes you don't have to have, by the way, relative extrema. Some functions don't have one. Okay. Also, now in math, like in many other disciplines, there can be many words that mean the same thing. The word relative sometimes is referred to as local. Okay. So when you hear the word local or relative maximum, it means it's the largest value within a certain region or neighborhood. When you have a relative or local minimum, it's the smallest value within that region or neighborhood. And also, the word global is also, or absolute is sometimes called global. Okay. So, okay, maybe I'll put together a little chart here. Um, a relative maximum is also known as a local maximum. Relative minimum is also known as a local minimum. Absolute maximum is also known as a global maximum. And then finally, an absolute minimum is also known as a global minimum, as you can imagine. Okay, just as a quick reminder. So the words relative and local mean the same thing. Absolute and global mean the same thing. Okay, so this is pretty common. You'll run into this throughout all of math. Many, or at least a few different terms that can represent the same idea. It's hardly any different than English, whereas there are many concepts or ideas or things that can be referred to by many different names. The same thing holds true here. So we're not going to take this too much further because, like I said, this is really more the subject matter of chapter 2, where we'll see how exactly to find these minimum and maximum points using what are called derivatives. For now, though, we just want to remind ourselves what this is all about. Now, here's an interesting idea, the idea that functions can be combined with each other. So algebraically, this is not terribly difficult. It's pretty straightforward, but there's some interesting ideas here too. For example, I can add functions, I can subtract them, I can multiply, and of course I can divide them as long as I avoid division by 0. All right, so here's some examples. F of x is x minus 2, g of x is x squared plus 1. I'm going to now apply all 4 operations to these 2 functions. Oh, and you also here you want to watch out for the notation. The reason why these are written twice is just to make sure it's clear that what's on the left and the right mean the same thing. The notation, the reason why this happens is because, math, let's face it, was invented by many different people over the centuries. And so some of them use one notation, some used another. So there often are many different ways of expressing the same idea. So here it's no exception. So this, for example, just simply means you're multiplying f and g together. All right, so the addition is very straightforward. You just drop the parentheses, combine the like terms, and you end up with x squared plus x minus 1. Okay. By the way, you'll probably remember that by convention, we always try to write the terms of an expression like this in descending order of the exponent. In other words, you wouldn't leave it like this. It's not that this is incorrect. It's just that we normally try to write the highest exponent first, followed by the smaller exponents, and then just save all the constants for last. You also might recall that because there's an x squared term in here, this is sometimes called the second order polynomial. The word polynomial has a very specific meaning, which we'll get to later on, but in effect, what it's basically is an expression where all the terms either are constants or the exponents are a positive integer. Okay, so that's referred to as a polynomial, which is taken from the Greek. It just means many terms or many numbers. Now, subtraction, of course, the big issue here is to be careful. We have to apply the distributive law, make sure that both of these terms become negative. Otherwise, we're just asking for trouble. Now you can see there's only two like terms, there are two constants. So when I gather these together, I end up with negative x squared plus x minus 3. And that's the way I would like to write it. We don't want to leave it like this, that's for sure. It's a mess. So we want to gather up, combine all the like terms, meaning constants go together, and the other terms are combined according to their exponents. And of course, then we make sure that the order is such that the highest exponent comes first, and we work our way down to the smallest exponents. Now here, we're multiplying. Now, there's a couple of ways. We have two, these are, by the way, referred to as binomial terms because each one has two terms in it. And when you have two binomial terms being multiplied by that, you can use FOIL if you want to. Our old friend FOIL. It's been a while maybe since you thought about FOIL. Oh, nobody forgets FOIL. Okay, so now it doesn't show here. So I'm going to do this in the next slide, just to remind you how FOIL works. It can be a very helpful technique, but unfortunately it's restricted, like I said, to the product of two binomial terms. All right, actually, let's move these over here. So the way this works, if you recall, here's f. The first term in each set of parentheses. Outer is these two. Inner is these two. And then last is these two. Now, there aren't any like terms here, so we end up with simply x cubed minus 2x squared plus x minus 2. So we have a third order or third degree polynomial, meaning it's a cubic expression. And we can't simplify it any further than that. Okay. Now, with the ratios like this, sometimes we can simplify it, sometimes we can't. In a case like this, I'm sorry, my mistake. It's x minus 2 over x squared plus 1. Unless x minus 2 is a factor of x squared plus 1 and we can simplify it, we would normally just leave it like this. Okay, and now here's where it gets interesting. We're going to actually combine functions with each other in a very interesting way. We're going to create what are called composite functions, which means that one function is a function of another function. So these are the two that you've probably seen before. We have this one is pronounced f of g of x. And this is the shorthand for that. And then you of course have g of f of x. And here's this symbol for that. And so what does this mean? Well, let's look at a quick simple example. Using the same two functions we were just using, let's define or find f of g of x and g of f of x. Okay, so f of g of x means that what you're doing is you'll replace all the x's in f of x with g of x. Okay, so in other words, since f of x is x minus 2, that composite function means the x becomes g of x minus 2, and g of x is, of course, x squared plus 1, which I'll put it here. And then when I combine them, I end up with x squared minus 1. Okay. Now, I'd like to point out that this is no different than, let's say, for example, evaluating this at 3. Because, again, here, all you're doing is replacing all the x's with a 3. Down here, you're replacing all the x's with g of x. Okay, so once you get the hang of this, it's very straightforward. Not that it isn't sometimes very messy, but this is how it works. And now we're going to do g of f of x, which means all of the x's in g of x are replaced with f of x. All right, so g of x is x squared plus 1. So now this f of x is squared. Now f of x is x minus 2. And so once again, we can apply FOIL. This would be your f. This would be your O. These two interior ones are your I. And then the product of these two is your last. So you end up altogether with, I'll put it over here, x squared minus 4x plus 4. Now, of course, if you notice, we have f of x squared, but then we also have this plus 1. So x minus 2 squared is x squared minus 4x plus 4, but then we need the 1. And so this is our final result right here. Okay, so you have to be careful. Yes, the f of x squared is x squared minus 4x plus 4, but we still don't want to leave out that 1. And that's the final result. All right. So now sometimes it may be necessary to evaluate a composite function and come up with a specific numerical result. How do we do that? All right, here we go. We got f of x is x plus 7, g of x is 2x squared minus 3x, minus 3 rather. Sometimes in this case, this can be thought of as the inner function. And this f is the outer, so-called outer function. So what you can do is solve for the inner function and then evaluate the result. So here, for example, we're asked for, let me just copy these. Well, actually, they're both here. So this is our g of x, and here's our f of x. And we're being asked to solve for f of g of 1. So this is a two-step process. We're going to take g of 1. Now, since g of x is 2x squared minus 3, g of 1 will be 2 times 1 squared minus 3 equals 2 times 1 minus 3, negative 1. All right, I'm trying to make it a little neater. Okay, so if g of 1 is negative 1, means this function, this is what we're looking for. Now I can simply rewrite it as f of negative 1. And we know how to do that. So all we have to do is go to our f of x and replace all the x's with negative 1. And we're done. That's it. That's the final answer. Now, this is not, of course, the only way to do this, but I think it's the quickest way. Okay, you solve for a numerical value for the inner function, plug that into the outer function, and you'll have your result. See that? So that's not that difficult. Well, at least as long as the functions are reasonably manageable. Oh, but then what about g of f of 1? Okay, let's try that one. So all of a sudden, g is the outside function, f is the inside function. So here's our same two functions. So what we need to do then is solve for this f of 1. So that's 1 plus 7, which is 8. And now g of f of 1 is the same thing as g of 8. And you can see that down here. Since g of x is 2x squared minus 3, we replace that x with 8, and we end up with 125. All right, and then sometimes we may find it necessary to find the domain and the domain of a composite function. So in this case, the domain of f of x is all real numbers except for 1. And down here, the value that would cause trouble for us here is 2/3, because that would leave us with 2 minus 2, which is 0. So we have to leave out 2/3. So there's a graph, by the way, there's a graph here of the composite function of these two. And let's see, the composite is this. So we end up with an asymptote. The bottom line is we end up with an asymptote of 2. Okay. So in other words, the domain is everything except 2. All right. And then finally, there's one more detail here we want to look at. Okay, there's one or two. Decomposing a composite function. So in other words, what if you were told that there's some function h of x, which is itself a composite function? You should be able to figure out what those functions are. In other words, given this function, it should be possible to break it up into these two, the outer and the inner functions. And so here, for example, if f of x is radical x minus 8, Ah, I think I wrote it in differently than they're doing here. Um, yeah, let's change this. Not that it really matters, but I want to be consistent with the notes. Um, okay, so in other words, this is the outer function, and this is the inner. And so we want to figure out what they are. And sometimes it's straightforward, sometimes it's not. So basically, in this case, since our original function is, then we could claim quite correctly that if we let, oh, geez, what did I do? H of x could be x minus 8, and then g of x could be radical 8. And you can see if these are our functions, g of h of x would mean radical h of x, which is radical x minus 8. And that means that this original function can be thought of as itself a composite function. It's not obvious when you look at it, but you can see that it's possible to decompose it into two individual functions like this. All right. Um, absolute value functions. So we just want to get a little practice with absolute value functions here. Imagine, now here's an absolute value function. I'll tell you, why don't we go look at it in Symbolab? That will give you a better feel for what we're supposed to be doing. Is it absolute 4x plus 1 minus all minus 7? That's on the outside. So if you look at the graph, you can see it does cross the horizontal axis at two different places. This one is the point -2, 0, and this is the point 3/2, 0. So that means, based on that graph, just actually, I'll just copy it. Why not? It just so happens I have this software on here called Snagit, which I was using a while ago. Basically, it lets you take pictures of what you're seeing on the internet. It used to come with Microsoft products, but now you have to buy it separately, I must say. And so, as they showed you, when you hover over it in the actual graph, -2, 0 is over here. We have 0. So in other words, what this is saying, and by the way, the function is absolute 4x plus 1 minus 7. So what that basically is implying is that when x equals -2, the function equals 0. And when x equals 3/2, the function equals 0. Okay, now we can prove it by plugging in those numbers. First, f of -2 would be, so we'll have the absolute value of -8 plus 1 minus 7. Now, the absolute value of -7 is, of course, 7, and that's 0. Now, 2/3, or 3/2 rather, looks like this. So 4 times 3/2 is 6. And we still end up with 0. So we know that these are correct solutions. The question is, how did we get them? All right, well, here's how this is going to work. Now, this is not the only way to do this. Um, we set this equal to 0 because that's what we're looking for. You notice how the function has been set equal to 0 because we're looking for the 2 points where the function crosses the horizontal axis, and this is what we're left with. Now, remember, because of the way the absolute value is defined, this implies that 2 things are true. And those things are, and once again, let me just put this on top so you can see it. That means that both 4x plus 1 equals 7 and the negative of that equals 7, which is the same thing as saying minus 4x minus 1 equals 7. Okay, so what we're doing is algebraically taking this expression and splitting it up into 2 pieces. Here, we basically just drop the absolute value signs. And over here, we multiply everything inside the absolute value signs by -1. And then we just solve for it the normal way. So here we subtract the 1, divide out the 4. And then over here on this side, the negative side, we add the 1 to both sides, and we end up with -2. And of course, we can double check if you think you've done it incorrectly. Well, you can double check very quickly and easily by simply plugging these numbers in and making sure they both result in a value 0. All right, let's do one more of these. So here's, oh, by the way, let's take a look at it. Symbol lab. 2x, absolute 2x minus 7 minus. Okay, so here's the graph. Why don't we snap a picture of it? All right, well, the computer is taking a break. I'm going to take a sip. Oh, it was over here. Okay. No, it's still acting up. Whenever this kind of thing starts happening, my first instinct is to immediately save all of my work because you don't know what's going to happen. All right. So let's see if it's willing to do something now. It's a wait. What do you know? Here we go. So now, interestingly enough, in this case, both of these points, right side of the vertical axis. So they're both positive, which can happen. And when we hover, the points are 1 and 6, 0. What we have to do now is show why. Why is this correct? All right. So first things first, what you should always probably do in these cases is simplify. I'll set this equal to 0 and then add the 5 to both sides. And now this implies that here 5 equals just 2x minus 7. On this side, though, it's 5 equals the negative of what's inside here. So you've got 5 equals negative 2x minus 7, or in other words, 5 equals negative 2x plus 7. So we do a little algebra on both sides. Here we add 7 to both sides. We divide by 6, 2 rather, and we get 6. Over here, we subtract the 7 from both sides to get negative 2 equals negative 2x. Oh yeah, what do you know? It works. So we found both of them. Okay, now we're just going to quickly discuss this concept of inverse functions. We're going to need this again in the future, of course. What does it mean for two functions to be inverses of each other? Well, you can think of it as almost like one of them offsets the effect of the other. The classic example of this would be, let's say f of x is x squared, and g of x would be radical x, square root of x. These are inverses of each other because if I take a number, let's say x is 3, and I apply f of x, I end up with 9, and then I apply, actually, let me be more specific about that. F of 3 is 9, g of 9 brings me back to the original 3. Okay, in other words, by squaring a number and then taking its square root, I'm just bringing it back to the original number. That's how I know that they're inverses of each other. Sometimes it's clear from their graphs that they're inverses, but not always. So there's a very interesting technique that will enable us to find inverse functions. Now, of course, it's not the only one. There's almost always many different ways of doing anything in math. But this one, I think you'll find it very interesting. And by the way, here's how you prove that two functions are inverses of each other. And also, I just want to remind you, notation-wise, this is going to refer to the inverse of f of x. F to the negative 1 is often used to represent the inverse of a function. What we're seeing here is that in order to demonstrate that they are in fact inverses, we need to show that the composite of the inverse with f is equal to x, which is the same thing as what I just showed you. In other words, applying, like if I started here, g of 3 is radical 3, and then f of radical 3 would be 3. So this is a numerical example of what you're seeing here. It looks terrifying when it's written like this, but this is all they're saying. F inverse of f brings us back to x, as does f of f inverse of x. All right, so let's, now here's a proof of that, which is the one I just showed you, but more formally, if f of x is x squared, g of x is the square root. By the way, this is of course the same thing. So here what's happening is that f of g of x means g of x squared, which means radical x squared, which is x. Down here, this would be the square root of f of x, which is x squared, and that brings us back to x. So here we have proof that those two functions are inverses. But what we haven't answered yet is the question is, how do we find these in the first place? In other words, what if we didn't know that these were inverses of each other? How could we take one and find the inverse? Oh, by the way, and these two are clearly 4x, 1/4 x clearly are inverses. All right, here we go. Now, you're going to find this, you might find this very strange that this works, but it does. Okay, and you can prove whenever you do one of these, this technique, you can prove your results. Let's say this is our function and we want to find the inverse. Here's one way to do this. Um, you start by writing it as y equals 1 over x plus 2. Okay, it's just easier if we call it y. Now, here's the wacky part, the part that you might not have expected. What we're going to do is reverse the variables. In other words, change all the y's to x's and all the x's to y's. And once you've done that, then you just solve for y. Whatever you come up with is the inverse of the original function. Oh, that seems very strange, but it's true. So algebraically, if x equals 1 over y plus 2, the first thing we do is multiply. And that brings us to here. And then you can see algebraically, you distribute x over these two terms, leaving you with yx plus 2x equals 1. Now I gather up, oh, here we go. I subtracted the x from both sides. I divided out the x, and this is my inverse. So f of x was originally 1 over x plus 2. F inverse of x is 1 over x minus 2. And you can prove that with that technique I just showed you. Here we start with f. I've got them two both listed here again. We're going to start by demonstrating that f inverse of f equals x. So that means I'm going to have 1 over f of x minus 2. Now, here's where we have to be careful. When you have a ratio of ratios like this, just remember, for something like this, dividing by a ratio is equivalent to multiplying by its inverse. Okay, that can save you a lot of grief. This little technique here, because it's easy to lose track of what you're doing. Like this 1 over x plus 2 is the same as 1 over 1 over x plus 2, which is the same thing as 1 times x plus 2 over 1. So what we have up here is just x. Oh, wow. Well, that was a mess, but we did it. And now we have to work this backwards. We need f of f inverse of x to be equal to x2. And so just a quick reminder, f of x is 1 over x plus 2. F inverse of x we showed is 1 over x minus 2. So therefore, one over f of x minus 2 And we end up with the same thing. So that means we did it correctly. All right. So there's just a few more things here. Let's just wrap up this section. Now, there's a second part, by the way, to this review. Um, it's here somewhere. I've got so much stuff open right now. The computer is very confused. So I'll tell you, let's not look for it right now. You can see it's getting crabby. Um, anyway, so here's an interesting definition. Functions can be even or odd. What is that supposed to mean? Well, if for every x, f of x equals f of negative x, the function is said to be even. If, on the other hand, for every x, f of x equals negative f of negative x, then the function is odd. So let's look at a couple of examples of this. By the way, most functions don't fall into either category. They don't have to. Some of them are even, some are odd. None of them could be both, of course, but many functions are neither. So let's try this one. By the way, here's a helpful hint. If the leading exponent, the largest exponent in your function is an even number, it's probably an even function. And if the largest exponent is positive, odd, then there's a pretty good chance that this is an odd function. That's kind of a hint. So if you look at this one, x cubed plus 2x, this one, if it's either, it'll almost certainly be odd. Okay, so let's see why. Now, first we can check it to see if it's even. That means that f of x must equal f of negative x. Let's find out. Okay, so here's our original function. F of negative x means each of these x's is being replaced with negative x. And that gives me negative x cubed minus 2x, which in turn means that negative f of negative x is x cubed plus 2x. And guess what? That means these are equal to each other. And that implies that this function is odd. All right, so again, let me just quickly remind you the definitions. This is even. And this is odd. What happened there? It disobeyed me, didn't it? All right, so that's odd. Even, oh, you can tell the computer is getting tired. Okay, so I just want to have them both there. You can see. So in other words, what we proved here is that f of x is negative f. And you notice how this is for every single x. It doesn't matter which one we choose. It'll always be true. And this implies that our function is odd. And like I mentioned before, we kind of already knew that it might be odd because the highest exponent is 3, which is an odd number. Um, let's try. Oh, by the way, this is what it looks like. How about this one? x squared minus 7. So already we sort of think that it might be even. It's almost certainly not going to be odd. It's highly unlikely that it will be odd. It could be even though. So let's demonstrate this. So the function, let's copy this to the next slide, is here. So what we're going to do is find out if so if you notice here, we start by testing for whether or not it's odd. Okay, so in other words, you've got the negative. All of this is f of negative x. You're replacing all the x's with negative x. And you can see it turns out not to be true. So that means we can rule out the function being odd. But can we rule out it being even? So basically with f of negative x, you're just replacing all the x's with negative x, and you end up with x squared. Oh yeah, it's the same. And so therefore, the function is even. Okay. Wow. And of course, this is just a parabola. Okay, so I've called this preview of calculus part 1. We still have to get through part 2. This will take another session or so, and then we can dive into limits. I know you've been dying to see the new material, and don't worry, it's coming. Limits, they start out fairly abstract. In other words, there's a lot of definitions going on. We try to explain what limits actually mean. But then fairly quickly, we'll be learning a large number of rules that we'll use to calculate limits. Now, there are some special cases that we will save for later chapters, but when we're done with chapter 1, you'll be in pretty good shape with limits. And then what we're going to do is use them to derive the results in chapter 2, where we introduce derivatives, which really is probably the most important chapter in the whole course, because really derivatives are at the heart and soul of almost everything we do in calculus. So we're getting close to being ready for this exciting new material, but I just want to make sure that you don't forget about all of these basic concepts, because we're going to need them quite regularly throughout the rest of the course. Okay, there's a lot of, I've been going through the notes, and there's a lot of concepts in there. The book, because it's a calc book, they're essentially assuming that you remember a lot of pre-calc. So I just want to make sure that that is in fact the case before we dive into the new material. So, it really can't be helped. But besides, we have 8 weeks, and so we might as well get all of this straight before we dive into the new material, which is of necessity a little bit more complicated than what we're doing here. So anyway, at the moment, there aren't any assignments. I think what we'll probably do is the first assignments will be based on limits, and that means that they won't be due for a while. God, at least a week, I would say. But what I will do is I'll make up a list. I'll let you know when they're ready, so you can start them as soon as you want to. But we probably won't be able to do them until we've at least started to cover limits. So for now, let's just keep going with our reviewing, but this should be done fairly quickly. All right, so anyway, I guess we'll stop here, and we'll pick it up again next time. And we'll wrap up a review of pre-calculus, and then we'll start to look at limits. Okay, so all right, I'll see you next time.